Hi, and welcome to how to draw Lewis-Dot structure of covalent molecules. This is example 2, CO2, also known as carbon dioxide. So before we begin, I just want to remind you, our goal is to go from a chemical formula like CO2 to drawing a structure that shows how the atoms in CO2 are connected, the types of bonds they're connected by, is it single, double, or triple bonds, and where the lone pairs are, which are the pair of electrons there in the molecule. So let's get started with this example. The first step in doing that is to count what's known as the total number of valence electrons from all of the atoms. So to get the total number of valence electrons in all the atoms, I need to figure out what atoms I have in my molecule and where they're at in the periodic table to get their number of valence electrons. So CO2 is made up of 1 carbon and 2 oxygens, right? Carbon, if I look in the periodic table, it's in group 14, so it has 4 valence electrons. And I have only 1 carbon. On the other hand, I have 2 oxygens, and each oxygen has 6 valence electrons because it's in group 16. So I'm going to take 2 and multiply it by the 6. So when I do that, I can do some mental math here. 2 times 6 is 12. Plus the 4 gives me a total of 16 valence electrons. All right, the second step says to construct a skeletal structure. So a skeletal structure essentially is a structure where you have just one atom that's in the center, and attached to it are all the other atoms in the molecule. Okay? So let's say you have 4 atoms, they will all be attached to it. Okay, that's what a skeletal structure is. And they're attached by single bonds, and there are no lone pairs yet. Sort of just shows you how the atoms are connected. So what we need to do in this example is we need to pick which one's going to be in the center. Is it going to be the carbon or one of the oxygens? The rules for picking which one goes in the center is the atom that's the least electronegative goes in the center. Now recall from Unit 3, electronegativity increases as you go across to the right. So that means that if you're looking at the periodic table here, we have carbon and here we have oxygen. Oxygen, since it's to the right of carbon, will be more electronegative. That means that carbon is less electronegative, and that means that carbon in this molecule is the least electronegative atom. So carbon is going to go in the center. So my 1 carbon goes in the center, and then attached to that carbon will be the 2 oxygens. Notice that the oxygens are attached, both oxygens are attached to the carbon. They're not attached to each other. So before we press on, I just want to note that here I added a couple of other sort of tricks that people use for picking the central atom. Electronegativity is the actual rule, but the rest of these are sort of tricks. So one has to do with the most unpaired electrons. If you draw the Lewis-Dot structure of a carbon atom, it has the most unpaired electrons, so it goes in the center. The other trick that's super helpful is typically in the chemical formula, the element that's written first goes in the center. So you notice that carbon is written first, so that one goes in the center and everything else connects to it. And the last trick is the atom that there's only one of. There's only 1 carbon and there are 2 oxygens, so carbon goes in the center. These are just tricks that are super helpful if you want to get quick access, but they don't always work. So you have to know this, the least electronegative goes in the center, because sometimes it just doesn't work out that the other tricks are correct. However, if you are getting tripped up, most of the time the atom that's written first or the one that there's only one of goes in the center, so you usually can use those, but it's not guaranteed. Okay, so let's move on. The next step says to arrange the remaining electrons, so every atom has 8 electrons, also known as an octet, around it, right? So none of these atoms are hydrogen, so they all want to have an octet. So let's take a look and figure out how many valence electrons we have remaining. We used 2 bonds to make the skeletal structure. Each bond has 2 electrons. So that means we use a total of 4 electrons. So I'm going to subtract that from the amount I started off with. I started off with 16 valence electrons. I used up 4. That gives me 12 remaining. So what I want to try and do is I want to try and give every atom here an octet. So how much does the oxygen and the carbon need to get an octet? Okay, so what I'll do here in a different color, I'll do it in greens, figure out how much does each one need, and I'll use X's to sort of keep track. So let's start with this oxygen here. This oxygen already has a bond attached to it, so that means it already has 2 electrons. So it needs 6 more to get an octet. This carbon has 2 bonds attached to it, so that means it has 4 electrons attached to it. So it needs, to get to 8, it needs another 4. And like the first oxygen, this oxygen also has 1 bond, so it has 2 electrons already. It needs 6 more to get an octet. So overall, this molecule would need a total of 6 and 6, so that's 12, plus 4, it needs 18. But I don't have that many, right? I don't have that many remaining. I only have 12 remaining. So what does that tell me? That tells me that my structure is, sorry, this would be 16, not 18 that I need. It tells me that my structure is going to need some double or triple bonds, okay? So in this example, since I'm going to run out of electrons, I need to make multiple bonds in my structure. So let's show you what that would look like. I'm going to redraw it here. Okay. Now what I'm going to do is to sort of show you how we can get that going there. I'm going to place on my terminal atoms the 12 electrons that I have remaining. So remember I had 12 remaining. I'm going to place those as lone pairs. And I look at my carbon, it still needs 4 more. So to get the 4 more on the carbon, what I'm going to do is just do some extra sharing. I'm going to take 1 lone pair from 1 oxygen and put it in between the oxygen and carbon here, and that will make a double bond. So now what we have, I'll make that bond in red so it's easy to see. We have a double bond there. And then this oxygen, that lone only has 2 lone pairs on it now. I'm going to do the same thing with the other oxygen. Again, I'm going to take one of these lone pairs on this oxygen. This oxygen has an octet, but this carbon needs a pair, so it has to do some extra sharing. Okay. And now I have a structure where every atom has an octet. We can always check that, of course. So if I were to check it, I would start it with this oxygen. I'm going to count how many electrons are around this oxygen. There are 2, 4, 6, 8. Remember, any bond that touches that oxygen, you would count each of those lines as 2. This carbon has 2, 4, 6, 8 attached to it, and this oxygen has 2, 4, 6, 8 electrons attached to it. So this is a good structure. Every atom has an octet. Now at the bottom here, there's information about how to calculate formal charges. We won't necessarily need to do that in these problems, but I will link resources for you. Okay, so just to quickly recap, the steps are pretty much the same. You start by counting the total number of valence electrons, and then you make your skeletal structure. After making your skeletal structure, figure out how many electrons you need to give every atom an octet, and compare it to the number of electrons you have remaining. So we needed 16, but we had 12. Since we needed more than we had, that meant we needed to do multiple bonds. And to make the multiple bonds, I took my skeletal structure, I added the 12 electrons that I had remaining around the terminal, or the atoms on the end, not on the central atom. And then what I did was I moved some of those into the middle to form a multiple bond in order so that every atom can get an octet. All right, hope you found this video helpful. Have a quality day.